So now we will discuss chapter 4. Chapter 4 talks about communication between an application and the operating system. So as we have been discussing, there are many methods: system calls, interrupts, exceptions, and signals. Broadly speaking, all of them go via the same mechanism. Of course, now for system calls, there is a more efficient mechanism. But let's look at the classical solution, and then when we discuss the implementation of the syscall instruction, we will then discuss the newer method, but it's broadly like this. So whenever you have an exception or you have a system call which is nothing but a special interrupt with the interrupt code 128, which is 0x80 in hex, or you have a hardware interrupt generated by a hardware device. So every device is given something called an IRQ, interrupt request queue, but we will discuss that later. So the moment any such interrupt is generated, what happens is that hardware interrupts have a full hardware architecture to collect them, queue them, buffer them, and then we have exceptions and system calls. So again, they have an architecture, but all of them are interrupting mechanisms. So if we just consider interrupts, every interrupt has a number which is called the interrupt vector. The interrupt vector is used to access a table called the interrupt descriptor table, and the interrupt descriptor table has the address of the handler. So similarly, you have a system call table. Similarly, you have an exception table. But system calls, as we have seen, have a single entry point. That's all right. That basically means that in this case, if you are using this mechanism, system calls correspond to the interrupt number 128. So you will go to entry number 128. This table is basically in memory, and the IDTR register, which is again a privilege register, has the starting address of the table. There you go to entry number 128. There will be an address. That address will be the starting of the system call handler. The address of the first byte of the system call handler. You will go there and you will execute the handler. The handler, as you have seen, will save the rest of the context. And this part is basically done in hardware, even though this table is populated in software. All right. But looking up the table and jumping there is all done by the hardware. And the reason is that you want the rest of the context to be stored by the handler. So you want the context to still remain alive, right? If you're running a program here, it can overwrite the context. So once this is done, you do that. Of course, the syscall instruction does not use the IDT, but it directly jumps to the handler because the address of the handler is stored somewhere, right? It's stored in a privilege register, so it directly goes there. So similarly for exceptions and so on, you have a code. Using the code, you access a table. The table is populated by software but accessed in hardware. Every entry of the table points to a handler. The handler is nothing but a function pointer. So you jump to that function and you start executing it. So what we'll do is we'll take a short detour and understand linked lists in Linux, because the point is that we are covering that part of the appendix that is needed in each chapter. So in this chapter, to especially understand the code, you need to understand how linked lists are implemented in Linux. Then only you'll be able to make sense of the code. So we'll spend around 2 slides understanding this. So what is the main idea of a linked list? The main idea of a linked list, you know. You have a next pointer and you have a previous pointer. That is the main idea of any circular linked list, that everybody knows who his neighbors are, left neighbor and right neighbor. But the point is that you want to create a generic linked list, and that's a different beast altogether, because the point is that you want to take any object and link it. All right. So let's say you want to take an object of type X, like some structure or some class. Of course, this is C, so you'll only have structures, and you want to link them. So typically, when you would write, let's say, a data structure code in your data structure class, you will create something of this type: struct, node. Then you'll have some int x, int y, whatever is the payload. Then you will have a node star next and previous. That is what you will have, right? But the point is that, if you look at this guy over here, our friend, he is clearly telling you this is not going to work. Because if you are creating a custom data structure, it is fine. Then you have node star next, node star previous. But if I want to create a linked list which is like a generic linked list which will work for all objects, how will you do this? Which means that object needs to have an whatever object type star next and previous. Which means any object, if you want to make it a part of a linked list, you'll have to do that. Fine, let's assume you do that. But how do you operate on it? Can you have one function that can operate on all linked lists regardless of the object? So that doesn't seem possible, right? So let us say I want to have something to traverse the linked list. That will need the type of the object. You don't face this problem in a data structure course because you have a single type of object. Now let us say along with node, there is an X node, and the X node is also part of a linked list. And I want the same function to take a node and an X node. How will you do? Correct. So to create a generic linked list, what is normally done in C++ and Java is that you, let's say, create an L list, a linked list, and make the type as the argument. All right. So then this is known as a template, but all of these things are not there in C. So you need to create something in C to create a generic linked list. All right. So what you do is that you create a simple structure list head, which has a list head as the next, and one as the previous. All right. As simple as this. Here the thing is that there is no payload. In the sense, the structure is not containing anything else, and you don't seem to have a problem with that. The reason is because of what we will see next. So this data or the payload will come, but let us understand how. Before that, we need to understand these two macros. The first macro is that I want to, it is a list entry macro which we will use in the next slide, but let us look at its arguments. A pointer, a type, and a member. All right. So the list entry macro is basically wrapping the container of macro, which is taking exactly the same three members, pointer, type, and member. We don't know what it does, but we know it's taking three arguments. This is a macro, pointer, type, and member. And list entry is the same as container of. So let us go and take a look at container of. So container of macro is defined here. So it takes a pointer, a type, and a member. So the first thing is it creates a void star pointer out of the pointer that is provided. There's a pointer that is, so what is a pointer? A pointer is a memory address. It can point to anything. So let it point to anything, we don't care. Okay, we really don't care. Let us create a void star out of it. A void star is what? A void star means it points to anything, I really don't care. So void star is a way of saying is just a pointer, I don't know what it points to. As simple as this. And a pointer is a memory address. If it's a 32-bit system, it's a 32-bit number. If it's a 64-bit system, it's a 64-bit number. All right. So this underscore m pointer, this is an internal variable which is of type void star, indicating that it's pointing to something, I don't know what, but its value is same as pointer. Fair enough. So the actual magic is happening over here. To appreciate the magic, let me clear off the ink. So what you do is that, let us say this is your pointer. You subtract something, correct? What do you subtract? You subtract the offset also. So now let us create a real structure and let us see. So let us say you are defining struct node. You have int x, you have int y. And then you have the struct list head. All right. So the pointer that I am providing is actually the pointer to this struct list head. So far, so good. Let us say that its value is 100. Then the value of this pointer is 100. The type here is basically struct node. And the member is LH. Alright, LH is the LH member of struct node. So the point is the value of M pointer is also 100. Alright. At this point, I make it 100. Offset of is offset of the member in the type. What is the member? LH. Okay. What is its offset? Its offset is if the starting address of node is whatever, X. So sorry, we have an X. So the point is, let's say the starting address is something. With respect to that starting address, where is the member LH stored? If you see, int X is stored at the address of node, Y is stored at address plus 4 because X is 4 bytes, and LH is stored at address plus 8. So let this be A. So the address of X is also A, address of Y is A plus 4, and the address of the struct list head is A plus 8. Clear? So offset of type member, so offset of LH from struct node is what? It is 8. Alright. So what this computes is what is the address of the node structure that is encapsulating the struct list head, which in this case is 100 minus 8, 92. Now what you do is you typecast this to type star, which is nothing but struct node star. So you return the value 92 with struct node star. So now if I were to summarize, what does list entry do? What list entry actually does is that given a pointer to a struct list head, it finds the address of its encapsulating structure using a macro which works in the manner that was described. There you find the offset and you subtract the offset from the pointer, where this is a pointer to struct list head. So you get the base address of the encapsulating structure, which in this case is struct node. So this means that wherever you embed a struct list head, you can always get the base address of its encapsulating structure without actually knowing what it was, given the magic of the preprocessor macros. So given that we have seen the list entry, let us move to the next slide and let's look at the fun. So in this case, a linked list is only made out of the struct list heads. That is all. So this is also a struct list head. So on and so forth. So you are creating a doubly linked list. All right. Now, so you first consider the simpler case, which is struct ABC. You have an int X and you have a list head list. So as you can see in this case, if I want to traverse the linked list, there is no problem. Given any list head, I can easily traverse, I can add, subtract, I can do everything, right? I can add an entry, I can remove an entry, I can do everything that I want. The reason is that I'm just working on struct list heads, which is generic. At any point, if I want to go to the encapsulating structure, I just call the list entry macro. As simple as that. So for example, if let's say my current node is current and I want to go to the next node, right? Not the list head, the node. So all I do is I call list entry, something that you have seen. So what was the format of this? Pointer, type and member. Pointer is current list dot next. So current, you go to your list, right? And go to next. Next means the next one. So if this is current, I come here. This is your pointer. The type is struct ABC, the member is list. So you can easily traverse a linked list in a generic manner using this little trick over here. So it turns out that we can do something that is even trickier and non-intuitive, which is normally not possible in other implementations of a linked list. So what you can do is to consider another structure which has an int X and a float Y. and then you have a struct listed list. So of course, I'm adding a float, but the kernel code does not have floats. So the kernel code does not have floating point numbers, but this is only for the purpose of demonstration. Let us say that I have a struct of type DEF, which is pointing to a struct of type ABC. This is perfectly allowed in this scheme because both will have a listed entry and they will point from one to the other. What I do is that a DEF can point to an ABC because let the current one be struct DEF star. What I do is I do the same trick, current list dot next. That's the pointer. But mind you, in this case, the trick that I play is the offset that I compute. Because I know that the next entry is an ABC, is that I compute the offset with respect to struct ABC and list. That gives me the correct pointer for struct ABC. This basically means that I can piece together, I can string together structures of different types. This is a very important thing, and we will see this in action when we discuss the signal handler. That actually structures of different types are strung together on the same linked list. You have to know their type. Assume you know that some way. Then it is possible to use the same trick that we just showed to actually dereference and find the encapsulating structure of the linked list. So this is a somewhat of a difficult and non-standard example. So what we are doing is that in general, we have structures of the same type on a linked list. But in this case, these are structures of a different type. They're not the same. So one of them is DEF, one of them is ABC. So assume DEF somehow knows the type of its next member. So maybe DEF has some information stored within it. So we don't care about the exact mechanism insofar as there is some way of knowing a priori. After that, you simply find the current list dot next basically gives you the pointer of the list head member within ABC. From this, you need to find the starting address of this encapsulating structure, which means you need the offset. For computing the offset, you need to know what kind of a structure is it and what is the offset of, what is the name of this member, the list head member. The macro will provide that offset, and then you subtract that from the pointer and you get the starting address of struct ABC, and then struct ABC is your encapsulating structure. This is quite complex, but we will see when we discuss signal handlers that this is exactly what is needed. So now we can go forward, given the fact that we have discussed some basic background, and the background is basic, but it's not easy. The linked list business for beginners can be quite complicated until they get a hang of it, because we are using macros. We are not actually using functions. So let's now do one more such basic exercise. So consider this simple piece of C code where all that I'm doing is I'm printing something on the terminal. So the hash include is something that we know. So the role of hash include is to essentially copy paste the contents of the header file, and the header file contains signatures. It never contains code. And the reason you need signatures is for correct compilation, because it has the types of the arguments of the functions and so on, which is needed for compiling. So stdio.h is essentially the signature for the standard C libraries input or output routines. That part is copy pasted over here. If that includes some header, that is also copy pasted. Finally, you call printf. Printf is defined in a dynamic library. It will be something like libc.so. version number 456. And most of the time, printf is defined there and it is loaded as a DLL, which means it's not a part of the program code. But when it is invoked, then the printf function is invoked. That part we already know. So it is deep inside the glibc library, but let us now go inside the code of glibc and see what exactly happens within printf, right? So we'll dive deep into the code of glibc, and then we will see how a system call is made and then do a deep dive into the kernel. So you can look at the code of glibc. Glibc is open source. So the format of printf is like this. You have a format string. So format string, you have seen this thing, right? It's whatever my name is. Then you give sort of a string pointer, and then maybe you can have something else for your entry number, so on and so forth. This is your format string, and then you have a variable number of arguments. So the format in C is basically int printf, where int is its return code, and the format string, and the list of arguments. So the format string is clearly a constant, which is why we have const, because it cannot be modified. And the ellipses, the 3 dots, indicate a variable number of arguments, which is dependent upon the number of percentages in the format string. The typical flow of control is like this, that printf calls some function, that calls some other function, that calls some other function. Ultimately, a system call is made, which is over here. So we will look at these functions. Broadly speaking, when you call printf, an internal version of printf is called __printf, which calls vf printf, printf positional, outstring, and put. So the signature changes and it becomes more and more generic, because you expect other kinds of functions also to kind of join here, right? Other functions to join at different points. So that is why they need to become more generic. For example, by the time you reach the vf printf function, things actually become bigger, in the sense that if you look at printf, what exactly is it printing to? It is printing to the terminal, right? The terminal is represented as a file in Linux. So in Linux, actually a file is both a regular data file, but even devices and terminals and so on are represented as files. So your terminal is a standard file called stdout. Stdout is your regular output terminal. Similarly, whenever you are doing a scanf, it is stdin, which is your regular input terminal. And for errors, it is stderr. All right, for errors. So what is happening over here is that when you are printing, you can print to either a terminal or a regular data file. So a regular data file will be fprintf, right? File printf. But be it regular printf or fprintf, finally everything will end up here. And since you want to generalize it, you are writing to a file where this is file *s, and the file can be the standard out, can be a regular data file, it doesn't matter. The first argument is what you are printing it to. The next argument is the format string. Then this is again another C internal glibc data structure, which is a list of the arguments, right? The printf arguments. And finally, some broad flags. So they basically say that, how do you want to write? So, these are flags that are used by the printing function to determine the printing behavior, right? Again, internal information. So the chain of calls, as you can see, has gone like this, from printf all the way to outstring and put. So what happens is that you have a massive chain, and it goes through a bunch of function pointers, and finally it goes to one function, goes to another. So a lot of functions it traverses. Names are not important, but let us look at the generic concepts that underlie a library designed like printf. Because what is the final job of a library? The final job of a library is to take your inputs, organize them, arrange them, manage them, collate them, kind of clean everything up, and then make a system call. So that is the job of a library, to enable the process of making a system call by cleaning up things. In this case, because there are like a family of printf calls, you make a generic function and kind of merge that entire family. So this is the broad view. So let us take a look at it. Don't look at the entire diagram. You'll not be able to understand it. So kindly follow my pointer. So we are abstracting things out as a file. std out is the terminal, in is the input, std err is the error stream, which again defaults to the terminal. Printf is what you call. Similarly, fprintf, sprintf, there are a bunch of printf family of calls. You call them. The generic version that prints to a file, all of them direct to the vfprintf function internally. Right? So names are not important, but the spirit is important. After this, so vfprintf is still taking what? It is still taking your the file name, the format string, and so on. What will be printed has still not been constructed. Right? So when you're printing something, you can write something of this nature. Printf value is equal to, right? Let's say x. Finally, what you will print could be val equal to 5. Correct? So this string has to be constructed. So after vfprintf, the printf positional creates the string that is printed. It constructs the string. Then outstring's job is to actually send it to a file where there are layers of abstractions. There are tables of function pointers because you can have different types of files. Finally, if let's say it is a system call, you prepare the arguments for the right system call, which means you put everything in the right registers and all of that. And finally, previously it used to be int x 080, but nowadays it is a syscall instruction. So finally, you issue or you make the system call. All right. So the job of the library ends here. So far, so good. After that, when you make the system call, then you know what happens on the other side, that it goes to a table. Well, let's look at the previous mechanism. The previous mechanism used to create a regular hardware interrupt. There it used to go to a table and a handler. But now syscall directly jumps to the handler. So syscall is no more treated as one of the other interrupts because it's clearly a special interrupt. So it kind of gets a little bit of business class service and it goes directly to the handlers. And then the handler takes over. So this is the logical separating point between the library and the system call. So we will discuss the internals of a system call next.
Let us now discuss the system call format in Linux. So we need to understand that a system call is a planned activity as opposed to an interrupt which can happen at any point of time. And an exception which is, well, technically it's not planned, but it is kind of between planned and unplanned, because unlike an interrupt, it can't come anytime. You execute an instruction and then that instruction might have an exception. But a system call is definitely something that you plan for in advance. That is why two registers, namely RCX and R11, they can be kept empty and they don't have to be internally used, right? So in a certain sense, we can think of these as caller saved. So we will find important uses for both RCX and R11, and we already discussed this in the previous chapter, that the return address and the flags are automatically stored by the hardware in these registers. So the assumption is that for the library, before it actually starts the process of invoking a system call, these registers, the contents of these registers are pushed to the stack. So the format is like this, that the system call number is there in register RAX. And we have seen a lot of system calls in Linux. And everything is, the number is stored here, which is the most important parameter. Then a system call can take 6 register based arguments maximum. So they are stored in the registers RDI, RSI, RDX, R10, R8 and R9 respectively. So of course you can have more arguments than this, but then they have to be pushed onto the user stack, and the kernel will then retrieve the values of the arguments from the user stack. So what a library function basically does, as we have seen, is that it basically enables in the invocation of the system call. So its job is to set up the arguments and call the syscall instruction. So the return value also has a format, the RAX register, that has the return value. So if we go to the OS side of things, so especially with syscall, that is kind of a shortcut, so it does not use the full interrupt mechanism. So in this case, there is an entry point which for x86 processors is entry 64.s. So what happens after a syscall? Well, we have already seen a large part of it in the last chapter, that the hardware stores a part of the context in RCX and R11. Then the remaining part of the context is stored by the dedicated software routine. In the entire process, interrupts are turned off. And finally, the do syscall 64 function is called. So this is like a standard entry point for processing all system calls. So for do syscall 64, the first thing that you do is that interrupts are enabled on the local CPU, because there is no point in kind of having an unresponsive system. So this is why, as soon as the state is saved, interrupts are enabled. And we access a system call table using the contents of the RAX register, which actually contains the system call number. So finally, what comes out is a function pointer of the system call. So we have been seeing this throughout the kernel, that we have a lot of tables that exclusively store function pointers. And these function pointers are basically the output of this process. And we also looked at system calls earlier. So just to do a quick recap, for the x86 architecture, you can always look at syscall 64.tbl, which has a list of all the system calls. A subset of these system calls are generic in the sense that they are architecture independent, like reading a file, writing a file, so on and so forth. So they are generic system calls, which are a part of the UAPI subsystem, and they can be found in unistd.h. But the full list is stored over here. So if we look at the first 12 entries of the syscall table, so we'll find all the usual suspects of the most common system calls that are made in any system. So read and write for reading any file, writing to any file. So kindly note that in Linux, stdout, which is the terminal, the one that you print to, that is also treated as a file. So is stdin, which is the standard input. So you read from it, that is also treated as a file. So every file prior to reading or writing, it has to be opened. Once the job is done, we close. Stat, fstat, lstat are different system calls for finding the status of different files. Poll, we will look at it when we talk more about interrupts. And lseek is basically a system call that is used to move to a certain position within the file. So what we have discussed earlier is that a file is a contiguous set of bytes, and any seek system call basically, if you're starting from 0, you can say that, okay, now I want to start reading from byte number 512. So a virtual file pointer will go there. So if we keep reading, we'll start reading these bytes. So that is what lseek does. Then mmap and munmap we have seen, which basically does what? That if you have a file stored on the disk and it's a sequence of bytes, then a part of this is mapped to the virtual address space. So which means that any access to a virtual memory will automatically get translated to a file access and vice versa. So basically a file and so if part of the file is mapped to the virtual address, and in a sense, it gets mirrored over there. mprotect is just to change the protection level of pages, make something read only, write only, and so on. So let's look at the write system call. So what happens is that, starting from the generic function system call handler to actually the function that handles syswrite, we have a long sequence of macros, which I said requires a genius to figure out. It's very long. And as I said, macros are there a lot in kernel code, and the reason is very clear. The reason is that macros basically do code rewriting at the pre-compilation stage. So they are very fast. So finally, we go to case syswrite where the system call is processed. So we need to understand one thing, that whenever we get into the kernel, the kernel is not obligated to start the process that, that got context switched, basically, the process that got interrupted. So the kernel will steal this opportunity and schedule anything that it likes based on all the processes in the run queue and, of course, their priorities. So let us now understand what exactly happens when the job of interrupt handling or system call handling or exception handling is done. At that point of time, we see if the current task has consumed a lot of CPU time or not. If it already has and it has exceeded its quota, then it is not supposed to execute anymore, and the scheduler is supposed to find another task to execute in its place. If there is a higher priority thread waiting that will displace the current task, then that also should execute after this. So for a variety of such reasons, the flag TIF need reshed can be set, which essentially provides a coarse-grained provides some coarse-grained information that there is a need to run the scheduler because most likely there is a process that is more suitable for running at the moment on the current CPU. So this flag itself is kept in thread info, which, if you would recall, was kind of an overflow data structure for saving additional process related state. The reason we needed this is because, if you would recall, you have a user process. If there is some event of interest, like a system call for instance, then there is a context switch. So it goes into the OS, and the same process actually becomes a kernel thread. So a different one is not started. It does its job, and then it either returns back to the same process, which is always good. Otherwise, there is a need to do a context switch. Now, when it is a kernel thread, it uses the 8 KB kernel stack, which, needless to say, has limited size. Given the fact that it has limited size, if we need to store more information, it has to be stored in a separate place, in a different place, which is the thread info data structure. That is where it is saved. And this is not stored on the stack. So it's stored separately in a different place in kernel memory. So there is a need to check this flag and figure out if there is a need to invoke the schedule function or not. If the scheduler needs to be invoked and the schedule function is the entry point of the scheduler, then you don't know which waiting task it will choose. It may either choose the current one or any one of these. And obviously, we have discussed many reasons why the current process or maybe another thread in the thread group should be preferred as opposed to an absolutely independent process, right? Independent user process, that's the expensive one. So we have discussed that in some detail. So the scheduler, of course, will take all of these things into account and the priority and basically make the best possible decision. If in case we are not going back to the same user process, then a complex state restoration has to be done, which is the reverse process of saving the state. The final instruction that is used to actually come back to user mode and start a user process, same or different, is sysret. So sysret is like the opposite of syscall. So after sysret, a user process starts to execute. So we will finish the first video of this chapter, chapter number 4 at this point. So in the second video or the next video, we will discuss interrupts and exceptions. And we'll also discuss the mechanisms in the kernel for actually running the interrupt handler. So we'll see there is something called a top half, there is something called a bottom half, and then there are many ways of realizing a bottom half. So we will discuss all of these things in the next lecture. But the current lecture ends here, where if you were to ask me to provide a brief summary, I will say that we discuss the broad interrupt exception system call handling architecture. We looked at a library, namely the printf library, in great detail, and we looked at the way that system call arguments are passed, and then the way that system call processing happens. Then you decide whether to call the scheduler or not via this flag TIF need reshed, and then of course the context is restored and you return. So a large part of this was regarding the context was covered in the previous chapter.